Okay, good morning again, everyone. Happy 97th anniversary of our Turkish Republic, also to everyone. Wish for many anniversaries like these. Um, okay, so today the plan is to finish ray tracing geometry, and then I'm going to talk about how we compute the color by using a very simple shading model. So ray tracing shading will be the next thing we are going to finish. And this week, I think tomorrow, we are also going to get the first assignment posted by your teaching assistant Bilgin. And therefore, it's good to complete as much as possible so that you can start your ray tracing assignment right away. Okay, so before we start, do you have any questions? Okay, no questions. So as usual, if you have any questions, you can use the chat box to write your questions, or you can just unmute yourself and speak up your question. Okay, so last time we were talking about ray tracing geometry. I talked about how we can intersect a ray with a triangle. A lengthy but a simple method was using ray plane intersection. First, we need to get the ray plane equation, and the way we do that is so here's the ray triangle. So on the slides, two techniques. Both of the techniques are described in detail on the slides as well. The lengthy but simple method is just using cross products to get the plane equation, then plug in the parametric ray equation into the plane equation to find the intersection point, which may be potentially be outside the triangle most of the time, because the plane that the triangle lies in is infinite. Okay, if our ray is not parallel to that plane, there will be an intersection point. So our ray is going to intersect the plane the triangle lies on. The plane is infinite. It's very big. It's infinite. So the only way where we cannot intersect, our ray doesn't intersect the plane, is where our ray is parallel to the plane. Okay. But if it's not, then there will be an intersection point. And then the question is, this intersection point, is it inside the triangle or not? So we just do an inside-outside test for a point in a triangle to finally come up with an answer, whether the ray intersects the triangle. If it intersects, we just report the intersection point. Okay, the other method uses what we call the barycentric coordinates. I'm going to write in the chat box barycentric coordinates of a point in a triangle. So it basically states that, actually this is not so big, it's like an implicit triangle equation. A triangle, any point, just consider any point inside a triangle. It's actually that any point inside a triangle is like a weighted average of the three corners, right? I mean, just let me go back to this GIMP. Okay, so let me draw a triangle here. Okay, I have three corners, A, B, and C. So any point P inside here is just like something, three different weights. Okay, let's call it WA times A plus WB times B plus WC times C. Okay, so this point P could be written as a weighted average of the three coordinates, because this is a linear equation. As you can see, all the points, they are linearly dependent on the corners. They lie on the same plane. And this, when I say it's like a weighted average of the three corners, what I mean is that these are really like weights, which mean that they are between 0 and all three of them, WA, WB, WC, all three of them are weights between 0 and 1. And since they're like a weighted average, also sometimes we may require that the summation to be equal to 1. So they're like percentages. This point P, how much percent, what is the percentage of A in point P? What is the percentage of C in point P? What is the percentage of B in point P? So when they're percentages, another requirement we have is they all add up to 1. Okay, their summation should also be equal to 1. So that's basically barycentric coordinates. We can write for any point to be a weighted average of the three corners when the three corners are known. This gives us an equation. We can use this equation to try to solve whether our ray intersects this triangle or not. One thing that you're going to see here is that although it seems like we have three unknowns, the degree of freedom. Now I ask you something. So any point inside the triangle can be represented by these three values, WA, WB, WC. Actually, on the slides, we're going to call them alpha, beta, and gamma. Okay, so I could do the gamma. So alpha, beta, and gamma. So these will be our weights. But basically, these fancy Greek letters, we are not, I mean, could have been anything. I mean, just some people, just when they see alpha, beta, gamma, I mean, it's like a difficult formula, mathematical formula. So it should be difficult, but they're just like WA, WB, WC. Okay, they're just weights. Here, but the triangle itself, we know that our ray is a one-dimensional object. Although it's a three-dimensional ray, we can parameterize any ray by just one parameter t, right? So look at the triangle surface. If you were living on a triangle, what would be your dimensions? Would you be living in a one-dimensional world, two-dimensional world, three-dimensional world? In other words, what I'm saying is that if you want to try to parameterize this triangle, actually this is a parameterization of that, how many independent variables do we need? You can write in the chat box. So what do you think? It's like when you're trying to show an address here. Can you indicate your position with just one scalar? Is one scalar enough to indicate your address on a triangle? Or would you need three of them? Yeah, two is enough. That's the correct answer. The two is enough because of these constraints. As you can see, this constraint basically tells us that one of them is 1 minus the summation of the other. Okay, we don't actually have 3 degrees of freedom. We have 2 degrees of freedom. If you fix WA and WB, WC is given. All right, you don't have a degree of freedom there. So the degrees of freedom we have on a triangle is 2. So that's why this is a two-dimensional surface, just like the surface of a sphere. Surface of a sphere could also be parameterized by 2. We didn't see the parametric surface equation, which we could have parameterized by using 2 angles. Or actually, we already have our GPS coordinates. We know on the world, any point on the world, ignoring the height, whether you're in a building or not. Any point on the world, it can be actually parameterized by 2 things like latitude and longitude. So just like that, a sphere, it can be parameterized by 2 angles, how high you are from the equator and whether you're away from the Greenwich, how far away from the Greenwich. So these 2 things, these 2 latitude and longitude, 2 angles, could also be used to parameterize a sphere with 2 variables. And just like that, we parameterize our triangle with alpha and beta, or alpha and beta and gamma. If beta and gamma is given, alpha simply be equal to 1 minus beta minus gamma. All right, so this is the barycentric representation, and by using this equation, we can also put our ray equation into this, and then solve the intersection. Now let's see. Here we have already seen. So this was the method. I haven't gone over the slides last time, but this is the method that I showed you on Monday, in which we first find the plane equation, and we find it by taking the cross product of this. After we have the normal vector of the plane, this gives us the plane equation. Saying that if you have any point on the plane and the normal vector, any point, the vector to this point and the normal their dot product should be 0. They should be orthogonal, and this gives you the plane equation, which actually, if you open this up, it will be the familiar ax plus by plus cz plus d type of equation. Okay, so this is the plane equation. And after we find the intersecting point, it could be P or P prime, whatever it is, we check whether it's inside the triangle or not. And in order to figure out if it's inside the triangle, if P is on the same side of AB SC, we can actually take a look at, if we look at this AB edge, P should be on the same side as P and SC here. According to AC, P should be on the same side as B. Okay, but also what you can say is, you could try to look at the directions. As I said last time, the cross products will give us the normal vector. When we do the cross product, it will give us the normal vector, and it will be the either the normal vector of the plane actually. If P, as you can see, P is another point on this plane. So when you do the cross product, C minus B, P minus B, for example, it should give you the normal vector. Actually, you can check that. Okay, if it's equal to the normal vector in all three cross products, but you should be very careful about the order of the cross product. If the direction of the plane is towards you from the slide, okay, then the normal vector is defined by a counterclockwise traversal of these vertices. In other words, the cross product C minus B, P minus B gives you the normal vector towards you, towards the outside the slide. If you do the P minus B cross product C minus B, you should get the exact opposite of the normal vector. So you can check whether these cross products C minus B, P minus B is equal to your normal vector in all three cross products. If all three checks out, then P is inside, otherwise P is outside. It's going to be outside. So this was the lengthy but simpler method. So the order of the cross products is important. So the other thing is that this is the barycentric method, barycentric coordinate method. These coordinates, alpha, beta, gamma, or WA, WB, WC, I like to imagine them as weighted averages, like percentages of the vertices that give us the point. Another way to think about those WA, WB, WC is to think about them as coordinates, okay? So if we have positioned our triangle on a non-orthogonal grid like this, we could have defined alpha and beta to be this. For example, when our point is between 0, beta should be between 0 and 1, right? Also, alpha should also be between 0 and 1 for the weights. When they're outside, as you can see, our points could be here. So this is another view of treating, semantically understanding what those weights are, treating them as coordinates. As I said, for me, it's more intuitive instead of thinking about them as coordinates, because these are not non-orthogonal axes. So it's not easy for me to think about them as coordinates, but thinking about them as weighted average, as weights in averaging is much simpler. Okay, so when we zoom in our triangle, we see that when, for example, beta is equal to 0, we will be somewhere along this line. So if you can also think about, see what, for example, what happens when weight WB and WC is equal to 0 and WA is equal to 1. We find ourselves at the corner. If any one of them is 0, for example, it's like those weights. You can also think about those percentages and weights as magnets that are pulling, trying to pull the power of the magnet that tries to pull the point towards itself. So when that power is 0, for example, if WC is 0, the power struggle will be between A and B. So the point will be on this edge. Whatever WA and WB is, our point will be somewhere along this edge. When WB is 0, then our point will be along this edge. When all of them are non-zero and they add up to 1, and they are between 0 and 1, our point will be somewhere here depending on those weights. Okay, so if alpha and beta are between these, then we are in this region. It defines actually a rectangle. We also need to have the third dimension, which is the triangle. And if also their summation is between 0 and 1, we limit ourselves to this one. And there is this hidden third coordinate gamma is actually about that third weight. So as a rule, in order to be in a triangle, as I said, alpha plus beta plus gamma should equal to 1. And this becomes the barycentric coordinates of a triangle. The implicit triangle equation simply be any point inside the triangle is given by these three parameters. Actually, we will just drop one of them. I think in the upcoming slides, we are dropping alpha, because since alpha is equal to 1 minus beta minus gamma, so we don't need to give it as a parameter, and instead right here 1 minus beta minus gamma, because alpha is equal to that number. Okay, if beta and gamma is given, we can directly find alpha. So it's actually, it will be a parametric line equation with two parameters. Now, here's the solution that we will do. We have two unknown parameters that are in the triangle equation, okay, for any given point, because we don't know the intersection point. For any intersection point, these will be known, but we don't know the intersection point. So when we plug in our ray equation into this implicit equation, there will be three unknowns in total: beta, gamma, and the race parameter t. So t, beta, gamma is unknown. Three equations, three unknowns. We will have three equations coming from, since these are vectors, this a, b, c. A, b, c are not scalars. A has ax, ay, az component. It's a three-dimensional vector. B is also a three-dimensional vector. C is a three-dimensional vector. Our ray is three-dimensional. So just what we will have is we will have three unknowns: t, beta, gamma, and three equations for the x, y, z coordinates. And we solve three equations, three unknowns. They will all be linear equations. After we solve for beta, gamma, and t, we will figure out if beta and gamma are both between 0 and 1. Again, the result of this could be give us something in which alpha and beta, or beta and gamma are outside this range of 0 and 1. In that case, it will mean that our point of intersection is actually outside the triangle. So this method, just like the original method, also tells us that if the intersection is inside or outside. Okay, so this is another way to view the barycentric coordinates. Those barycentric, those weights actually also, as I said, it's like three magnets pulling each other in a power struggle. These alpha, beta, gamma values. Another interesting thing is that that weight, actually, the weight of C, is exactly equal to the area of this region over the total area of the triangle. So if it can pull, so this is the pulling power. If C can pull that point towards itself with a really larger weight, what will happen is that this area AC is going to increase. And the largest it can be, I mean, if C can pull this point all the way to this vertex, AC will be equal to A. In that case, we will have gamma equal to 1. All right, so you can also consider, if you can know how to compute these areas, you can also compute. By the way, actually, we will be needing this, I think, for certain things. For a given, we will need this later in texture mapping, I guess. So here, we don't know the point currently in intersection. We know A, B, C. We have 3 unknowns. We have a ray equation. We know. We try to find where ray is going to intersect the triangle. But consider the reverse problem, in which the point's coordinates are already given to you. If somebody gives you the coordinates of the points, XYZ coordinates, from that, can you find out what beta and gamma is? The way to do that is you can do it by using these area ratios. Okay, if you know the point coordinates, you can compute the area, you can compute the area of the triangle. There's, what was the name of the law? With just the 3 coordinates of a triangle, you should be able to compute its area, right? I mean, you can also use, for example, cross product to do the same thing, actually. The cross product, the magnitude of the cross product with 2 edge vectors of a triangle gives you the area of the parallelogram if you divide it by 2. So the magnitude of the cross product divided by 2 gives you the area of the triangle. So you should be able to figure out these AA, AB, and AC. You can also find the total area of the triangle. From that, given a point's coordinates, you can also find what alpha, beta, gamma is. But here, our problem in this intersection test is that we don't know point P. We are trying to find it. But what we have is a ray equation and the ABC vertices of the triangle. All right, so this is our equation. These are the constraints. If point is inside, their summation should be less than or equal to 1, and they should both be non-negative. We plug the ray equation into this, and this is what we get. Okay, so if you look at this highlighted part, this is my point P. The point P is the ray's origin plus T in some direction. This is my ray going in some direction. And this is A plus beta, B minus A. So these are arranged in such a way that the weights, I mean, we take the parentheses of beta. So beta is multiplied by B. It's also multiplied by minus beta is multiplied by A. Remember, 1 minus beta minus gamma is the coefficient of A. So the coefficient of A, which is alpha, we write it as 1 minus beta minus gamma. If you multiply this with A, what do you get? A minus A beta minus A gamma. So if you put the beta and gamma coefficients into here, like this, you get this equation. So this is, as you can see, 3 unknowns. In this single equation, we have 3 unknowns, T, beta, and gamma. But this is not actually a single equation. These are just, all of them are 3-dimensional vectors, which gives us 3 equations like these. Okay, so these are my 3 equations. I have 3 equations, 3 unknowns. We solve a linear, we go back to our linear algebra days and try to figure out what they are. We can rewrite the coefficients in matrix form. These are the unknowns that we need to find. These are the coefficients of that linear equation, and these are the results. You can either find the inverse of this matrix, or you can use the Cramer's rule for that. So it's basically linear algebra, but you don't need to memorize these formulas. So the Cramer's rule says that beta is equal to the determinant of this 3 by 3 matrix divided by the determinant of A. So if A is equal to this, the determinant is given by this length formula. Actually, it's not, you don't need to memorize this. It's like the determinant is like this. You cross out, just like it was cross product, right? The determinant was, we used it when I described you the cross product. The determinant is, if you cross out the column and the row, it's E times E minus F times H. That's the coefficient for A. Then we come to D. When we cross, actually it's crossing out, you will get the same thing, but this crosses out rows one by one. So if you cross out this and this, you get D times E, G times F. That's it, but with reverse, with negative. So it's minus B, DI times DI minus GF. So that minus is put actually inside by changing their order. And you cross out C times D times H minus E times G. So it comes by using the determinant of a 2 by 2 matrix. You can actually figure this out. So after that, after we have these, if you know how to compute the determinant of a 3 by 3 matrix, it becomes just plugging them into this to find beta, gamma, and t. This is how we can do that. All right. We find t, beta, and gamma gives us, we want the intersection t to be larger than 1, right? Our t min here is 1. If you want the intersection to be in front of the image plane, we hit the image plane at t is equal to 1. So we are looking for intersections that are larger than 1. If you may also impose on your scene a distance which you can see farthest. So this is sometimes called the far plane, or in games, for example, this is also a parameter that you set, the far distance. Even Minecraft, for example, you can set this, the far distance play. So how far do you see? Sometimes you may use this for efficiency in rendering, but in ray tracing, we don't need this actually. Okay, now I'm going to show you the code that implements the ray triangle intersection, which is this. So intersect triangle. As you can see, this you may ask yourself, okay, how does this solving 3 by 3 matrix and all these determinants, how is it faster than the cross product one? Cross product seems like a shorter method to me, but computationally, actually, this just involves lots of additions. We do less multiplications. Although it seems lengthy in terms of code, it's much more efficient than the cross product. Okay, as you can see up to here, we all have subtractions, additions. And this is the place where we do some multiplications. So this is EIMHF, simply means that EI multiplied by HF. And this EIHF comes from that determinant slide, A, B, C, D, E, F, A, B, C, E, F, G, H, I, J. So these are our determinants. I pre-multiply, compute them, and then this big M becomes this, T becomes this, gamma becomes this. So it's just, you don't need to memorize. You can use this code as is if you want in your assignment. So this is how we have the intersect triangle implemented in C. All right, it's just the implementation of what you see on the slide, nothing more. Okay, you can even make it, maybe you can, I don't know, maybe you can make this even more efficient. I'm not sure. I didn't try to optimize this code. I just wrote whatever I have seen on the slides. I just turned it into C statements, and that's it. All right, now let's continue. So this actually concludes the geometry part of ray tracing. And in some complex models, we may have a lot of triangles. So this is an example in which there are 725,000 triangles. And it's not only the triangles that makes this bunny look nice. As you can see, the color along the surface varies. It's actually, it's not constant, or I mean, it not only varies in terms of shading, but some parts are of the material is different. There are whitish parts, brownish parts. So what we call such a surface, we call such a surface textured. In order to increase the quality of our renderings, we are also going to see how we can specify color along the surface variably, not just saying, for example, if you have a sphere, you will say in the next part, we are going to say how we can define our materials. We are going to say, okay, this sphere is a red sphere, it's shiny, or it's matte, it's reflective. So we will give these properties, the material properties, to the surface. But when I say when I give a same material to the entire surface, it will look like the figures we generated, like this. Okay, it will look like this. So this is you see different shades of yellow here, but it's still the entire sphere is the same material property. In order to have a figure that looks like this bunny, we need to give variable materials to different parts of the surface, and this is called texture mapping. Sometimes you can even do the material mapping could be done. I mean, you may want, if you want, texture mapping is the simplest way. You're just varying the diffuse color. But what if you want to change shininess, matteness of the surface in different parts? Then you need to have yourself a material map. You're not going to see that in this course. In this course, we're just going to see how we can vary the color, the diffuse color of the surface along the material. So this is another model which is composed of 9.2 million triangles. So therefore, we need to, so this one is, there's no texture mapping here. As you can see, this is just a grayish, same property along the surface. A dragon model composed of 5.5 million triangles. We are going to intersect our arrays with all of them if we don't subdivide the scene into different parts. Obviously, you see the need to optimize this ray tracing. We need to have a data structure for our scene to speed up ray triangle intersection tests. There are lots of, your ray is going to probably intersect with 1 or 2, maybe 3 triangles. Okay, your ray is, if it's piercing through this model, for example, it will be intersecting 1, 2, 3 triangles at most. There may, if in the scene with a single object. Okay, and when it's piercing through this dragon, for example, it's going to enter the dragon at one triangle, exit the triangle in the other triangle at the back. So we are going to use the intersection with the front triangle that will have a smaller t value, but just 2 triangles. Out of 5.5 million triangles, our rays intersecting with 2 of them. So testing with all 5.5 of them is 5.5 million of them is really inefficient. So we need to devise ways to index the scene, put a data structure on the scene to get rid of unnecessary intersection tests. So this is the armadillo model. Again, it's not texture mapped. There's a single, it's gray colored throughout the same material, and 7.5 million triangles. Wow, this one is 116 million triangles. So you can have really large triangle models. And if you look at the intersection cost, if you have 1 million triangles, and if you want to generate an image of size 1 megapixel, it will make 1 trillion intersection tests in total. So that's why ray tracing, with no optimization, ray tracing is really slow. Another thing you can notice is that in addition, for optimization, I'm just thinking about ideas for optimization. One way is to have an index structure on the scene. Another thing is, if you have noticed, ray tracing is what in parallel computing people call embarrassingly parallel. Okay, so this, when something is trivial to parallelize, this term embarrassingly parallel is used. And ray tracing is, I think, such an algorithm because if you have noticed the main loop of the ray tracing in this main function, we are treating every ray independently from the other rays. I mean, when we compute a pixel color, we don't make use of any information about its neighbor's color. Every ray is processed and its color is computed independently of the others. So these 1 million rays, they are all independently computed from each other, their color. Therefore, we can just, if you have a parallel machine with 1,000 cores, 1,000 nodes, you can give, or 1 million of them, you can just give the ray tracing computation to each of them in parallel. They're independent from each other. So you can parallelize ray tracing easily. But one thing you need to be careful about in this parallelization is that all of these parallel workers, they should be able to access the whole scene. I mean, the scene definition, the triangles, 100 million triangles, they should be able, you should have some kind of a shared memory architecture, or you need to have an intelligent way to send the scene information to a certain group of rays separately. Okay, so these are just things about making ray tracing efficient. Okay, and in order to have realism, we can put environmental maps. So look at this blurred background image. It makes the scene look really real, right? It's like we're really taking a photograph of something. And this may be nothing but a blurred photograph that is texture mapped onto a rectangle at the behind. Okay, so all these reflections, shadows make ray tracing very realistic. Okay, so that's the next thing we are going to talk about, how we can, first of all, how do we do shading? And the things that we are going to see is to compute the color along the surface, varying with respect to the light's position. So we are going to have a simple shading model, and then we are going to also learn how to have reflections and shadows. So the shading part, those slides are composed of 3 components. First, computing the surface color by thinking about the interaction of that surface point with the light source just individually. Then thinking about whether the surface point is in shadow or not. How can we implement shadows? And then the last thing, which is actually the property ray tracing is different from the other forward rendering pipeline algorithm too. It's the property that gives the ray tracing its name. The reflections of other objects on this surface point. We will do that by tracing the ray, by following the ray from this to that, this to that. So that the name of the algorithm comes from the ability to have reflections of objects on surfaces. Okay, so these are the 3 parts that we are going to talk about in the next set of slides. All right, let me just start those second set of slides. They are here. Yeah, shading. Okay, do you have any questions up to now? Oh, this is the PDF one. I need to get the PowerPoint. Yeah. All right. So let me start this. Okay, so actually, we've just finished the ray tracing geometry. So right now the algorithm looks like this, as also seen in the code that I show you. For each pixel, we compute the viewing ray. We just keep track of the minimum intersection of parameter t of that ray with objects. For each object in the scene, we test the intersection of our ray with that object. If that intersection happens, and also if the intersection's t parameter is less than the intersection that is discovered up to now. For example, if we have an intersection in which t is larger than 1, but if there's another intersection in front of the intersection that we just found, the one that is actually in front dominates. So we only update t min if the intersection is smaller than the discovered intersection up to now. Okay, if that is the case, then we update our minimum t, and we also say that this is the object that we intersect. So this is important. Okay, not only we maintain the intersections ray where the ray intersects, we also need to say which object are we intersecting with. Because if it's a triangle, the color computation would be different because the triangle surface normal at that point is computed differently. Triangle has a constant normal along the triangle surface. If it's a sphere, the normal changes along the sphere surface. So I need to know which object it is. Not only for normal computations, also I need to get the color of the object, the material properties of the object. So I need to keep track of the object that I'm intersecting with at that t min. And after this, so this is actually the costly part. This for loop takes the entire large part of the computation, where we intersect our array with all of the objects. And at the end, if this object not null means that our array actually intersected with some object. And at that point, we just set the pixel color for that pixel to the color of the object. And this is the simplest case. I mean, if we do this, it will look like this. I haven't shown you in the code actually. Let's now comment out this part. So close this object color. So what we mean is, if this is the part where it says, okay, all these indentations, or I don't know, maybe I edited somewhere else and Notepad++ does not recognize those tabs. The indentation is all off. So this is the part which it says that the object O is not null. If there is an intersection, so this is the part actually we do lots of color computations that we're going to see today. But what I mean is that without knowing shading, this is the best we can do right now. I'm going to show you image RGB. Sphere, we just set the pixels RGB color to the sphere's color. Okay, let's see what kind of an image we have right now. Where is my Ubuntu? Yeah, all right, so that's right here. Okay, so let me compile this. Ray tracer, it was the simple version 1. v1.c, yeah. Oh, okay, I forgot to link the math library, so don't forget -lm if you're using square root. Maybe, I mean, C++ automatically does that, maybe. Anyway, now I'm going to run it. Ray tracer version 1. It needs a camera file, simple camera, and simple scene. Okay, it ran, and let's see the image it generated. Somewhere here. Yeah, this is the image we generated right now. Okay, so this is the image we got. Okay, so this is if you just know ray tracing geometry, you can see your scene right now with like this. Okay, this is a yellow. They're all just, I mean, if you just write this hundreds of lines of code just to display these disks, I mean, it doesn't look very nice, right? I mean, you could just do it in Paint easily. Now, the important part that gives the power to ray tracing will be the shading part. We don't want all same yellow across all the rays that hit the sphere. Some of these yellows should be dark, some of them light. We should have shadows. And at the end of the day, our version is going to look something like this. Do I have, yeah, actually, simple PNG. Yeah, it should look something like this. Okay, at the end of the day, when we have actually the positions of the spheres have also changed, but we just there are no reflections here as far as I can see. It's all simple shading model plus shadows. I also ran, we have also two triangles, which gives us this table beneath, because without the table, shadows do not show. I mean, we can have shadows. For example, what you see here on the red sphere is the shadow of this yellow sphere on it. Okay, so this is the shadow of the yellow sphere. As you can see how binary it is. It's not soft shadow. It's when something is in shadow, we only have the ambient component which we are going to see. But it makes the scene, look at this shiny spot. That's the specular component. There is the diffuse component which makes us to give different yellow amount to different parts of the sphere. There is also this specular component which gives this shininess, and it will change where the camera is looking at. When you move the camera, that shiny spot is going to move on the sphere, but the diffuse components, they're not going to change. So we are going to see this in the shading part of ray tracing. So let's go back to the slides. And we are going to have our break soon in a couple of minutes. So yeah, the image looks like this. This is a lower resolution image, but we have seen how the image looked like if we just assign the color as is. So much work for this bad image. We didn't use a realistic shading algorithm. Now, here, I'm going to actually quickly go over these sets of slides before the break, because it actually talks about how the shading really happens in real life. So it's lots of details about the physics of objects material, how it interacts with light. Reflectance is the thing when light rays come to an object, based on the material properties, it reflects. There's some power. Light sources have power distribution, and objects' material surface have reflectance distribution. So actually, the color we see is a interaction of these two things. Okay, so these are, as I said, too much detail, unnecessary for our simple model that we are going to use. This is, if you're interested in computer graphics and to actually do something better than the simple model that we are going to use in this introductory course, you may want to learn these material, because this really shows how real, what is the physics of in reality what happens. So, as I said, we already know the object color occurs as a result of the interaction of the reflectance properties of the object and the power or intensity of the light. And there are different reflectance power cones. So I'm going to skip this one. So the spectral ray tracing, actually, instead of using our simple model that I'm going to introduce, it uses accurately model this reflectance and power interaction of the light with the surface. This is a more realistic modeling of what's going on in real life. So if you want to accurately render more higher quality colors on your scenes, you may want to take a look at spectral ray tracing. You're not going to do it in this course. And we are going to simplify this a lot. We are going to represent, instead of using the wavelength, we are going to use our color will be composed of three components: RGB, how much, and the reflectance. Each material, a surface, will have reflectance coefficients. Its color, for example, the color of that yellow sphere, I'm going to indicate it like this: 0.1, 0. For example, if I want it to be yellow, I want it to be 0.9, 0.9, and 0.1, for example. 0.9, so this one, let me write it in the chat box. So if these are the reflectance, 0.9, 0.9, 0.1. Okay, so look at this vector. This can be the reflectance coefficient, so the color of the surface of my yellow sphere. It's a value between 0 and 1, because it tells us, the reflectance coefficient tells us how much of the red component of the light it reflects. So 90% of the red component is reflected. This is what it means. So we will indicate color as real valued numbers between 0 and 1, and it will indicate how much of the incoming light is reflected. Its red component is reflected. For example, let me ask you a question. If I have a yellow sphere and the light in the environment is not white, the light is blue, pure blue light, what color I will see that yellow sphere? You can write in the chat box, 1 or 2 answers will suffice. So let me, again, another question. I have a blue light. So this actually, the question I'm asking is, I haven't talked about it in the slides yet. Okay, now we have talked about, yeah, exactly. The answer is black, because there is also the light in the environment will also be represented with the RGB model. For example, if we have a white light, we are going to indicate its power as, it may be actually large numbers. It doesn't necessarily be between 0 and 1. We may say, okay, 100, 100, 100. My light is I have a white light with power 100, 100, 100. So then when that light comes, we reflect, our reflectance coefficient is going to determine what color we see by multiplying these two vectors together, but it's not cross product or dot product. I don't know whether that product between two vectors has any name. It's actually, the result is another three-dimensional vector in which we just multiply the individual components and we form a new vector. For example, if the light, I'm again writing in chat box, if the light intensity is 100, 100, 100, okay, when I multiply it with my reflectance coefficient, the color that I'm going to see is going to be 90, 90, 10, all right? So this 90, 90, 10 is computed by multiplying this 100 with, so 90% of this 100 is reflected, which makes 90, 90, and 10%, 0.1 of this 100 is reflected. So the color along the surface will appear to us in this color 90, 90, 10. Okay, it's still a yellowish color. So my question was, if I have a pure blue color, what would we see? So the blue color will be something like this, 0, 0, 100, that's blue, right, RGB. And if you do the same multiplication with this 0, so it will appear as 0, 0, and 10, which is very close to black, by the way. So it's you can also, if you're answered, instead of answering black, if you're answered, actually, black is correct answer, because I didn't tell you that the blue component was 0.1, right? I mean, if it's a pure yellow sphere, it shouldn't have any blue component. It should just have 0.9, 0.1, or 110. I mean, a pure yellow, nice looking yellow sphere would be 110. And in that case, if you multiplied 110 with 0, 0, 100, you would get 0, 0, 0. So black will be the resulting color. So this is how we're going to interact the light intensity with our material color. All right, now I think it's a good time to have a break. So already 4 minutes passed. So let's have a 10-minute break. Let's meet at 10:45, okay, quarter to 11. We will meet in 10 minutes to continue with this simple illumination model. All right, I will stop sharing and I will stop the meeting. See you in 10 minutes.